Swayam Prabha. Digital India. Educated India.
Hello student, welcome back to this course on optimization method. So in the last class we discussed about genetic algorithm. So last two classes we discussed about genetic algorithm, and I have introduced you what is genetic algorithm, and then I also gave you the flow chart of simple genetic algorithm, and then I have discussed the genetic operators. That is your selection operator, crossover operator, mutation operators. Then I have discussed the different genetic operators. So mainly selection operator, then crossover operator, then mutation operator. So this I have discussed in the last class. Today I will show you one hand calculation and I will explain the different process of genetic algorithm through hand calculation. So far whatever we have discussed that I did not discuss how to generate initial solution or how to create initial solution. So today I will discuss that one, and then we should evaluate all these solutions, okay, and these solutions are evaluated using a fitness function. So I also explained that one, and then I explained the termination criteria. As I said, I can take maximum generation as a termination criteria, or if the function value is not changing for some generation, maybe 20 generation, maybe 50 generations, okay. So if these values are not changing, then also I can terminate this loop. That means already I got the optimal solution. Like the classical method, so where we generally evaluate the gradient. If gradient is near to 0, then we stop this iteration, but here we are not using any gradient information. If the fitness value of the base solution is not changing with time, that means you can conclude that you have already reached the optimal solution, or you are not getting any improved solution, and therefore you can stop the iteration. Then selection operator, as I said, the main function of the selection operator is to create multiple copies of the better individual, okay, and then you are eliminating the inferior solution. The worst solution anyway it will be eliminated, and some of the inferior solutions will also be eliminated here. And then we have discussed about crossover operator. So what crossover operator is doing? So it is creating new solution. So as I have explained that crossover operator is creating two new solutions near the parents, okay. So you are basically doing the local search using crossover, and then you are applying mutation, and mutation is also creating new solutions, but it is trying to explore the other region. So what crossover is doing? Basically it is trying to converge to an optimal solution, and the mutation is basically trying to diverge it and going out of the optima and trying to explore the other region basically. So this is the function of selection, crossover and mutation, and then you will continue this iteration or generation till you are not meeting the termination criteria, okay. So this is the simple genetic algorithm. Now what may happen that when you are applying crossover and mutation, so at that time what may happen, that some of the solution, suppose even the base solution or better individual may be destroyed. So what may happen? So I have written here the crossover and mutation may destroy the base solution of the population pool. So sometime it may happen, it is not that crossover and mutation will always create a better solution than their parents, but sometime what may happen, they may create some inferior solution, but at that time you need not worry, because when this solution will go through the selection operator again, this solution will be eliminated by the selection operator. So, if any inferior solution is created by crossover and mutation, then what will happen? That will be eliminated by the selection operator in the next iteration. So, what I want, that my better individual, which is the generation based individual, that is not destroyed by crossover and mutation, and in order to preserve those things, so I can actually use elitism. So, what is elitism? Elitism is basically you are preserving the base solution, the better solution you are preserving, that is basically called elitation. So, I want that some of the better solution, they will not go through the crossover and mutation, they will directly go to the next generation. So, so that we can preserve it, and that process is known as elitism. Okay. So, I have defined here what is elitism. Elitism is the preservation of the base solution of the population pool. Basically, I am preserving those solution, and I can implement this elitism by percentage or in number basically. So, what I can do, that some percentage I can preserve, maybe 5%, maybe 2% of the base individual. So, that can be preserved and they will directly go to the next generation, or I can also put a number that okay, I would like to preserve 10 individual, the base 10 individuals. Okay, so, they will go to the next generation without participating in crossover and mutation, because the crossover and mutation may destroy that solution. So, apart from selection operator, then crossover operator and mutation operator, we should also use the elitism. So, just to preserve the better individuals, and so that they are not destroyed by the crossover and mutation operator. So, I hope this is clear. So, with this actually, so I will also put one operator, and that is elitism somewhere. Okay. So, I will put elitism. Okay. So, elitism I will put it, and this is another operator. So, where we are just preserving the base individuals. If I compare the Nasser to the computer mapping. So, in Nasser, so we are using this nomenclature. Suppose we are using population. What is population? Population is nothing but a set of solution. Then individual, this is a solution. Okay. So, in set of solutions, so this is a solution and we call it individual here, and in computer we are called a solution. Then fitness, so we call it fitness. It is nothing but the quality of a solution, that is your fitness, and we call here chromosome, and here this is encoding of a solution. So, you are actually converting in case of binary coded GA, you are converting it to a binary bit. And what is gene? We call it gene, and here it is a part of the encoding solution. So, we are using this nomenclature. Now, let us solve one example problem. This is a very simple example problem. We have only one optimal solution of this particular problem, and so I will solve it here. So, with using hand calculation only, and then I will explain the different process of genetic algorithm. So, the problem is, it is a maximization problem, and it is a maximization problem, and the function is f x equal to sin pi x, and x is between 0 and 1. Okay. So, x is between 0 and 1, and if I plot this, the solution is 0.5 somewhere here. So, this is 0.5, that is the solution, and optimum function value is 1. Okay. So, solution, if I solve it, so I should get x star is equal to 0.5, and then function value at x star is 1. Okay. So, this is the solution. Now, we will try to get the solution, and basically I will complete one iteration of genetic algorithm to solve this particular problem. Now, before that I have to take couple of decisions here, or now, so I have to convert this continuous variable x to binary bit. Okay. So, for that I have to take a decision what should be the bit length. Okay. So, what should be the value of L, this I have to define, the string length I have to define. Now, the how to define that? So, I have given this equation. So, this is the mapping we are using basically. So, to convert a real value to binary value. So, I can use this mapping, and I said that. So, this is showing the precision. Okay. So, what type of precision you want basically. Now, if I say this is my precision, epsilon is my precision here, and now I need, suppose I need the precision of 0.01. So, in that case, so what is I max? I max is 1, and then I minimum is 0 and 2 to the power L minus 1, and if I solve it for L, so I am getting L equal to 6.658. So, that means to get a precision of 0.01, the string length should be 6.65. So, you cannot use 6.65. So, you have to use 7. So, in that case you are getting your precision will be little bit more than 0.01. But here what I am doing, because this is a hand calculation, if number of your string length is more, then it will be little bit complicated. So, what I have done, I have considered your a 6-bit string. Okay. The 6-bit string I have considered for this particular problem, but you can also consider 7 as I said, or if you want to have more precision, then what you will do, you will increase this the string length, okay, 7, 8, 10. So, you can find out. So, what may happen, suppose if you are using 0.00001, then what should be the string length. So, I can calculate it here, 1 minus 0, and this is 2 to the power L minus 1. So, if I solve it, and I will get the required string length. So, from here I can find out what should be the value of L. Now, what will happen? Certainly, it will be more than 7 now. So, okay. So, I need your more bits in order to increase the precision. So, here what I am doing, as I said, so I have used 6 bits. Okay. So, 6 bit, and 0 0 0 all 0 means this is 0, and all 1 means it should be 1. This is the mapping I am using using this equation. So, here what precision I am getting? So, I am not getting 0.001, but I am getting a precision of 0.0158. So, this is the precision I will get. Okay. So, then this is the first decision you have to take. Then the second decision is the population size. So, what should be the population size? Now, question is that suppose your string length is 6. So, you can use around 8 to 10 times as population size. So, maybe around your 40 to 60 something like that you can use. So, now what will happen if you are using less number of population, suppose you are using, if your string length is your 6, but you are using 4 or 5, then what will happen? Mixing will not happen. So, crossover will not be able to find new solution after some time. So, therefore, population should be little bit large. Now, question is that if it is a large population you are using, so 100 population, then what will happen? The computational time will increase, because 100 population means 100 function evaluation in each iteration, the 100. So, if you are doing it for 100 population and 100 iteration, you just see 100 into 100, this mass function evaluation you are doing basically. So, your computational complexity will increase. So, therefore, it should not be too large, okay, and it should not be too small also. So, depending upon the complexity of the problem, if your problem is highly nonlinear and then you have multiple optimal solution, and in that case you should use more population. Okay. So, population size should be more, but this is a hand calculation. So, therefore, I have used only 4 population. So, in this case I use population size of 4. So, this is a hand calculation. So, therefore, I have just used population size of 4. Population size of 4. Now, let us solve this problem using genetic algorithm, okay, by hand calculation. So, what I have to do now, the first step is initialize population. So, you have to initialize the population. So, you can do in two ways, you can initialize the population. The first one I am just giving the algorithm. So, how you can do, you can write a computer program to do that, but the concept is something like this. Suppose I would like to generate this string randomly. So, means I want that this is a random generation of this string. So, what I will do, I will do, so I have to generate 6 bit, and I have only 2 options, that the bit may be either 0 or 1. So, right now you are at the first bit, okay. Then what you will do, you will just take a coin and toss it. If it is head, then you put 1, if it is tail you put 0. So, in this case suppose head, I am getting 1. Then you go to next bit, you toss the coin, in this case it is tail, so you are getting 0. Then go to the next one, you are getting tail, this is 0, then head, this is 1, then this is tail, you are getting 0, and this is head, you are getting 1. Okay. So, this way I can generate a random string. You can also write a computer code. Suppose what I can do, I can generate a random number between 0 and 1. If the number is more than 0.5, then I will put 1, and if it is less than 0.5, then I will put 0. So, I can generate this string randomly. So, similar way I will generate the second one also, okay. This is first solution, second solution, then third solution, and then fourth solution. So, this is one way to generate the binary string. Now, there is another way, I will explain that one also. Now, next is what you will do, you will find out the decoded value, okay. So, you will calculate the decoded value, and decoded value is 37 here, and for this is 12, and that for this is 58, and this is your 46. So, how we are getting 37 here, this is your 1 0, okay, 0, then this is 1 0 1. So, this is 2 to the power 0, then 2 to the power 1, then 2 to the power 2, okay, 2 to the power 3, then 2 to the power 4, and 2 to the power 5. So, all are 0. So, here 2 to the power 0 means this is 1, and then anyway this is 0, okay, because it is 0, then this is 4, and this is your these two are 0, and this is 32, okay. So, you are getting 32 plus 4 36 plus 1. So, we are getting 37. So, similarly you can also calculate the decoded value for solution 2, that is coming 12, then for 3 this is 58, and for 4 this is 46. Then you calculate the real value. So, real value I have used this mapping here, and so I can find it out. So, how I am getting 0.58, 0.587. So, this is x I, which is equal to x minimum. So, x minima is 0, then plus that x maxima is maximum value of x is 1, and then 0, and this is 2 to the power 6 minus 1 into decoded value. So, decoded value is 37. So, then if you calculate this thing, so you should get 0.587. Similarly, for if you put decoded value of 12, then you should get 0.19, then this is 0.921, and this is 0.73, okay. So, you are getting the real value. So, now this is one way to initialize the population. So, you initialize the population as a binary string, then you get the decoded value, and then you find out the x value. I can also do in a reverse order. So, what I can do, I can generate this x value randomly. So, what is my upper bound and lower bound? I know that lower bound is 0 and upper bound is 1. So, I can generate the 4 solutions between 0 and 1, and this solution I can do, and then using the equation, using this mapping equation. So, I can find out the decoded value, and once you are getting the decoded value, so corresponding binary string you can find out. Okay. So, you can find out. So, you generate this randomly now. So, what we are doing here, we have generated the binary string and then we are doing the decoded value and then x value, or otherwise what you can do, you generate this x value randomly and then decoded value and then you calculate what is the binary, you find out the binary string, or you calculate the binary string. Okay. So, there are two ways I can do. So, either binary string randomly I can generate, or I can generate the x value randomly and then corresponding binary string I can generate. Okay. So, this is the two ways I can generate the initial population. Now, next is the calculation of objective function, calculate objective function value. So, objective function value you just calculate it. So, what is your function? The function is that f x is equal to sin pi x. Okay. So, this is your function. Getting my? So, if you put the x equal to 0.587, then you should get 0.96. For 19 you should get 0.56, 0.921 you should get 0.25, then 0.75, and then you calculate the fitness function, that is, this is the objective function and this is small f is objective function and capital F is fitness function. So, if you recall that this problem is a maximization problem. So, therefore, I can take that f equal to small f, that means the same function I can use as an fitness function. So, here what will happen, if the capital F value is more, in that case the solution is better. But if you have a minimization problem, suppose as I said that minimization of f x. So, what you can do, you can write this is maximization of f which is equal to 1 by 1 plus small f. So, I can also use this function. Okay. So, but in this case I will not convert it because this is a maximization problem. So, therefore, I will just use that small f or equal to capital F. Okay. Fitness function is equal to capital F and which has actually same value. Okay. Now, the next step is selection operator. So, you apply selection operator. So, in this case I am just doing one iteration. So, I am not telling about the termination criteria, but you can check whether you are getting the optimal solution or not. So, in that case you can terminate, but here I am just showing one iteration. So, therefore, you just go to the selection operator. So, in this particular problem I have used proportionate selection. Okay. So, you can also apply tournament selection, or you can also apply rank selection, or you can also apply your roulette wheel selection. Okay. Here I am using proportionate selection. So, what you are doing? So, you calculate the relative fitness. So, what is relative fitness? So, relative fitness is that sum of all this fitness. Okay. So, you divide this by sum of all this fitness. So, therefore, the relative fitness you are getting 0.38, then 0.22, then 0.1 and 0.30. Okay. So, this is the relative fitness you are calculating. So, if you recall, this relative fitness is equal to the area occupied on the roulette wheel. Okay. So, this is the area this particular solution will occupy on the roulette wheel. So, this is 38%, then 22%, then 10% and 30%. So, now the expected count will be selected. So, what is expected count? That means 38% of 4 will go to the next generation, or expected count, that is. So, 38% into 4. So, 0.38 into 4. So, you should get 1.53, then 0.22 into 4. So, you are getting 0.89 and this is 39 or 0.4 and then 1.19. So, this is the expected count, and then you calculate what is actual count. So, actual count, as I said, that this is the expected count, but you have to have a integer value. So, it is for that. So, actual count will be, so for 1.58, so I just round this to the higher one. So, this is 0.2. So, actual count will be 2, then here it is 1 and here it is 0 and then 1. Okay. So, what you are getting here, the first solution, that is the base solution, and this solution will have 2 copies and then this one will have 1 copies, and third one is the worst solution. So, it will have 0 copies and the fourth one will have 1 copies. Now, if you recall, what is the function of selection operator? Selection operator is creating multiple copies of the base solution or better solution, and the worst solution has been eliminated. At the same time, we are also maintaining the total population size. Population size was 4 and now also you are getting total 4 population, that is 2 copies of the first solution, then second solution 1 copy and fourth solution 1 copy. So, you are getting 4 solution. So, that way we are implementing the selection operator. So, as I said, I have done it using proportionate selection. You can also apply rank 1 or you can also apply tournament selection. The next step is the crossover operator. So, you have to apply the crossover on the solution on the mating pool. So, if you look at what is the mating pool is whatever you are getting after the selection operator. So, now I have 2 copies of the first solution, this is 1 and this is 1, 2 copies, then I have 1 copies of this solution and I have 1 copies of this solution. And I am just writing what is the decoded value. So, this is 37 and this is 37 and x value is 0.58 for here and 58 for here and this is 0.19 and 0.73. So, this is the solution on the mating pool. Now, how to apply crossover? So, you take 2 solution from the mating pool and then you apply crossover operator. So, that has to be done randomly, that means you have to select the solution randomly from the mating pool, then they will go for crossover with a crossover probability of PC. As I said that PC I can take 0.65 to 0.95 or sometime 100%, but in this case I am taking 100%, that means all the solution will go for crossover. And then you have to do it randomly. In this case I have selected that the first solution will go for crossover with the second one, and similarly 3 and 4 will go for crossover. So, in order to implement crossover, so what you have to do that you have to select a crossover site. Okay. So, you just select a crossover site and this crossover site to be selected randomly and between 1 to L minus 1. So, in this case between 1 and 5. Okay. So, you select a side. So, I got it randomly, this is 3 and for this is 2. So, this is the crossover side, okay, after 3. So, therefore, the new population will be that first part of the first solution, this part, and then the second part of the other solution. So, what I am getting, the first part of this solution, that is 100 and then 100. So, you can see that 100 and 100 you are getting, and then first part of the second solution and second part of the first solution, that is 001 101 001 101. Now, when you will go for crossover of the third and fourth solution, then crossover site is 2. Okay. So, this is the crossover site now. So, what will happen? So, this is 10 and this is 10. So, therefore, once you are swapping up, so you are not getting any new solution. Sometime it may happen like that, but anyway. So, here I am getting the crossover site of 2. So, therefore, first solution will be this is 101110. So, 101110 and the second solution is 100101. So, 100101. So, in this case you are not getting any new solution. So, whatever the earlier solution you have, the same solution you are getting after crossover. So, sometime it may happen also. So, therefore, what we want basically, so we want to maintain diversity in the population pool. So, I explain about the selection pressure. So, what will happen if suppose if you are increasing the tournament size. So, what will happen, your population will be saturated by the base solution, then base solution. So, what will happen, so if you are picking two solution for crossover, then there is a probability that you may get the same solution. Okay. So, then if you are applying crossover, so you are not generating any new solution. So, therefore, I want to maintain diversity in the population pool. So, therefore, you should not use higher tournament size, 2, 3 is fine. If your tournament size is more, so in that case your population will be saturated by the base solution. So, whatever we have done, so this is a single point crossover. Okay. So, this is a single point crossover. So, you can also apply multi point crossover. So, multi site crossover you can use, but in this case I have done single point crossover. Now, let us see whether we are getting better solution after crossover. So, here this is the decoded value 36 and 0.57 and F value is 0.97 and capital F is also 0.97, and then this is 13 and then this is 21, then 0.60 and 0.60. Anyway, so you are not getting new solution here. So, you are getting the same solution that is your 0.73 and 0.587 or 0.59. So, you are not getting any new solution from your third and fourth solution, but from first and second solution. So, you are getting two new solution. Now, if you look at this particular solution, so you just see the decoded value of these parents was 37 and 12, 37 and 12 was the decoded value, and here you are getting a decoded value of 36 and 13. So, that means the crossover is creating a solution near to their parents. So, you are not getting a solution from 37, you are not getting 58, or or from 12 you are not getting your 5 or 6, something like that. So, what you are getting? You are getting a solution near to the parents. Okay. So, therefore, what crossover is doing? So, crossover is creating a solution near the parents. So, slowly it is going towards the optima. Now, the next step is to implement mutation. Okay. So, crossover operation has been done. So, let us apply mutation. Now, this is the population after crossover. So, I got 4 solutions. Okay. So, these are the 4 solution after crossover, and this is the decoded value of this crossover, and this is the x value of this crossover, real value of this crossover. Now, what we will do basically, so how to apply crossover operator, that you have to take a crossover probability Pm. So, as I said, the Pm should be very your low value, it is a very low value. So, generally what we use that 1 by L. So, in this case suppose I am using 1 by 6. Okay. So, this is the Pm probability, mutation probability I am using here, and then what you will do basically. So, first you will go to this particular bit, the first bit, and then you generate a random number. If the random number is less than 1 by 6, then you mutate it. Okay, mutate means use a sense, if it is 1 then you make it 0, and if it is 0 you make it 1, or otherwise you just keep it. So, that way then you go to next one, then go to next one, and then go to next one, like that. So, in this case what is happening? So, in this case what is happening, for the fourth bit, that random number is less than 1.6. So, this bit will be mutated. So, I have used 1 by 6, it means that out of 6 trial, so 1 will be mutated. Okay. So, out of 6 trial 1 will be mutated. So, in this case the fourth one means suppose it will be mutated. So, similarly, so fourth one will be mutated. So, here it is 1, so it become 0, and for the second case this one will be mutated. So, this is 0, this will be 1, and for the third one this will be mutated. So, therefore, this is 1, so it is 0, and the fourth one this will be mutated. So, this is 0 and this is 1. So, you are getting a new solution. So, you can see basically, just see Now, this is the decoded value of the mutated solution. So, 32, 45, 38 and 45. So, if you look at for the second solution, this bit has been mutated. So, this been mutated means you are adding 2 to the power 5 here. So, in this case the decoded value is increased by 2 to the power 5. So, therefore, it was 13, now you are getting 45. Okay. So, that means 32 you are adding. So, here you just see it is not creating near the parents basically. So, if I say that this is the solution before mutation, and after mutation you may get a completely different solution and maybe at a different place. So, therefore, what mutation is doing? So, mutation is trying to explore the unexplored region in the search space. Okay. So, here it is it is not creating a solution near to the earlier solution. So, now you just look at that. So, I am getting 32 here. So, this is 0.51 and then f value is 1 and this is 1, and if you look at for other solution also I have calculated the small f and capital F. Anyway, capital F and small f are equal here, and your average value it is increasing to 0.878 and maximum value. Okay. So, the solution is 0.50, but anyway for 51 also you are getting approximately the function value of 1, that means you are almost near the optimum. Okay. So, if you look at that after crossover and mutation, the average function value is increasing. So, and maximum function value is also increasing after crossover and mutation. We have solved one problem. So, I can also do one more iteration. So, with this solution in the population. So, now you can apply selection operator again. So, if there is any inferior solution, that will be eliminated by the selection operator, and then you can apply crossover and mutation again, and probably after some iteration your solution will improve, or you are marching towards the optimal solution. So, today I have explained genetic algorithm using hand calculation. So, I hope the process is clear to you, how we can apply the crossover operator, the mutation operator, then the selection operator. We have to use some programming language to solve a problem using genetic algorithm.